Okay, in this set of slides, I'm going to show you basically some eye candy to inspire some different ideas for map making, talk a little tiny bit about encoding data to symbols, but not a lot because we did talk about this quite a bit earlier, just talking about data visualization. It's all the same principles dealing with points, lines, polygons as it is with maps. Okay, so organizing your data. Imagine you have a bunch of rainfall data at weather stations across the US. How could you deal with that? You've got specific locations, and then you've got a range of values, quantitative, continuous data, measuring rainfall at a bunch of weather stations. You know, what could you do? What can you vary? We've talked about this a lot. You might start with points, and then you could change them according to size, or you could change the color according to the variables, right? And then how would you group the values? So, you know, maybe you have 2,000 weather stations. You're not going to give each one of them their own individual color or their own individual size. They'd be indistinguishable from one another. So this is kind of what we talked about in the last couple sets of slides, classification, etc. So we've talked about all of these things in our regular data visualization. You've got tools at your disposal. You know, we've got orientation, which might be better for wind direction or things like that. Color, shape, value, texture, size. You need to think about what kind of data you have. Is it quantitative? Is it qualitative? It's going to really impact the way that you encode your values or your data. And just for some examples, this is population distribution in Martinique, total population. That's why they used proportional symbols and not choropleth. Choropleth can be used for population density, people per square kilometer. And you can see it's fairly consistent, but you wouldn't just put the total population in here when you're using choropleth. Here we're doing two things. The population is being encoded in the size of the circle, but the color of the circle is reflecting the median income. So we're doing bivariate here, more than one variable. This is, they're calling it population potential. This is a density map, basically. I mean, it looks like they've got an algorithm that they laid out here, but creating some kind of a model predicting, I don't know what population potential is in this case, but a density map. Here, they're mapping the result of some analysis. So here we've got median income per region, and then they're using the red line, the thickness of it and the color, to map the discontinuity or the difference between the income. So where do we see, if we're taking an aggregate median income per aerial unit here, what is the discrepancy or the difference between the neighboring counties? I think that's a pretty cool way to do it. It's something that you can discern maybe by looking at the map, but this is a kind of a redundant encoding that gives you more direct information. I think that's pretty smart. Another thing, we've talked a lot about divergent color ramps and how you would use them, you know, to maybe represent positive and negative, or, you know, positive standard deviations, negative, or, yeah, I wanted to move you past positive and negative and show you this map where it's household income, but the two different colors represent whether it's above or below the state's mean of mean income. So the mean income is 36,641, and so anything green are counties that are making on average above the median income and then below. I think that's a smart way to do it. It gets you out of the positive and negative. I want to show you the difference between a heat map and a hotspot map. So sometimes we call heat maps hotspots. Heat maps are density maps. So you have a bunch of observations of a certain thing here. You create an observations per square kilometer and then map it in a raster format. Hotspot map is a statistical analysis where you're showing clusters, statistically significant clusters of high values associated with that data set in red, and then statistically significant clusters of low values that are associated with that map. So it's very different than a heat map, which is just a density map. These are statistically significant clusters. It is up to the user to define the neighborhood over which these clusters are relevant, but that's not what this class is about. Take the advanced class, advanced GIS. Okay, another problem is using coordinate systems that blow up states like this, underrepresent states like Hawaii, and even just within the United States, we have some states out on the East Coast that are so small that the information about them gets lost. And the alternative to that is to use something like a hexagon map. We all know what the shapes of the United States are. We know, relatively speaking, how big they are. So by converting them to a consistently sized and shaped hexagon, now we're being forced to focus on the quantitative differences that are being mapped. And this is another way to map a raw count, because instead of showing the values per some arbitrary state size, we've normalized the state size, and now we are allowed to show some kind of a raw count because it's not being biased by how big the state is. So yeah, suicide rates here in blue. So we have gone ahead and normalized this value. It's per 100,000 people. But at the same time, how interesting is it to show the percent change? We still have data from 2014 to 2016, but if we wanted to look at the percent change from 1999 to 2016, you have to make a calculation to make that happen. But here we're using a diverging color ramp and showing states that are showing a positive increase, which is a little bit of a misnomer, and a negative increase, percent change, negative increase, a decrease over time. Oh boy. So it's not just about how you're encoding the data, but the story that you're trying to tell with the data, and how can you make that easier to ingest, right? This gives us a snapshot in time. This shows us change over time in one static image. Okay, I showed this before using 3D to extrude values. You can do it at polygon level as well. Just notice that this really does make an ugly map, so I would not recommend that. And then getting into bivariate stuff, how many things are being encoded here? Again, so we've got the state we're encoding population change, so an increase or it doesn't look quite right, so let's just keep moving. On top of it, we have either graduated or proportional symbol, I'm not quite sure which, showing a live birth rate over time, and then the change is the color, either an increase or decrease. So 3 different things being encoded there. Here is another way to encode, and notice that this is using subtractive color. So we have, let's see here, what does this say? High school graduates maybe in pink, college graduates in yellow, and I don't know, medium, some kind of income. Reading, writing, and earning money. So income down here. So areas that are very pink must have a higher proportion of high school graduates. Yellow have a higher proportion of college graduates, and then it's being offset by the blue, which is the amount of income being earned. I find this really hard to read because these two things are kind of related, and this is different, but the colors are equally very different. So what they've done here is they've tried to pull out some of the counties and kind of help you break it down a little bit, and they've got 2 attempts at a legend. I think that the triple whammy here is what makes it difficult. You guys are going to get an opportunity to make a bivariate, just 2 choropleth map. It's going to be very similar to this county level, where you're going to have low to high. In this case, they're mapping obesity rate against food insecurity. So we've got low to high food insecurity. This is much easier to read, I think. You can say to yourself, okay, so what's going on with this big cluster of black counties? These are, I guess it's dark blue, high counties with very high food insecurity, which means, whether or not you have reliable access to enough food for a healthy, active life, and high levels of obesity. That's what's happening in these dark blue areas. The light areas are low obesity rates and low food insecurity. Blue would be low obesity rates but high food insecurity rates. Does that kind of make sense? And then high obesity rates but low food insecurity are all the yellow states here. So this is a really great map, and I'll give you a big fat data set that you can use that has a ton of variables in it, so you can kind of plot up any number of different relationships in a bivariate choropleth map like this. Cartograms, these are becoming much more readily doable in ArcPro and ArcGIS. There's little scripts that will make these for you really quickly. The idea here is that it's kind of like the hexagon, where instead of having to normalize to put a raw count, you're changing the area of the unit to reflect the value. So this one is CO2 emissions. So you don't have to convert it to a rate. You take the raw count and then you blow up or shrink down the area depending on the value that you're trying to map. Okay, in Tableau in particular, we've talked about the coordinate system. It really sucks, but it's very easy to make choropleth maps. You can do point distributions, make heat maps or density maps. It is possible to make flow maps, but getting the data to do this is really complicated. We haven't had any success in previous semesters. Proportional symbols and spider kinds of maps. So just as a little bit of a teaser for things that you can do, and hopefully you'll be inspired to do something fabulous for your final project.